Hello, friends. Today we are exploring the surprising new findings and new truth about the white dwarf stars. These dead stars were once thought to be completely sterile, but the new research suggests they could host surprisingly common, long lived habitable zones. Discover how planets could survive the star's red giant phase and find a new home in the faint glow of the white dwarf. So this video is going to be very interesting, and don't go anywhere because we are going to explore this very idea. Let's go. Hello everyone and welcome back to our cosmic journey. Today we are diving into the question that might sound like science fiction but is rapidly becoming a serious topic in astrobiology. Could we, or any life for that matter, live around the white dwarf star? Well, to answer this question, let's explore this further. For billions of years, life on Earth has thrived under the warm, steady glow of our sun. It's a yellow dwarf star, stable and reliable. When we imagine other habitable worlds, we often picture them orbiting stars much like our own, bright burning furnace that provide constant source of energy. But what if I told you that some of the most commonplace, unlikely places in the universe where the life can exist are also the remnant of the dead star, and they could be surprisingly hospitable. This isn't just a thought experiment. New research is revealing that the white dwarf stars, once considered cosmic graveyards, could harbor remarkably common and long lived habitable zones. And the implications for the future of life in universe are truly mind bending. To understand why this is such a surprising idea, we first need to understand what a white dwarf star actually is. Imagine our sun. It's currently in its prime, fusing hydrogen into helium in its core, but that's what we call a main sequence star. These stars, like everything else, will have a life cycle. For stars roughly the size of our sun, this cycle is quite dramatic. In about 5 billion years from now, our sun will run out of hydrogen fuel in its core. When that happens, it won't just wink out, instead, it will begin to swell dramatically, expanding into a red giant phase. It will grow so large that it will engulf Mercury, Venus, and possibly even Earth. The surface will cool, the sun surface, giving it a reddish hue. This phase, and it certainly doesn't sound like a good time for any life or on the nearby planets. After this red giant phase, the star sheds its outer layer, forming what is known as a planetary nebula, a beautiful glowing shell of gas. And this is what is left behind. At the very center is the star super dense core. This is our white dwarf. It's incredibly hot initially, but no longer undergoes any nuclear fusion or fusion reactions. Instead, it slowly, gradually cools down over the trillions of years, essentially radiating away its leftover heat. For a long time, white dwarfs were considered cosmic relics, fascinating but ultimately barren, and for good reasons. Think about the challenges. Starting with, the first one is their size. A typical white dwarf is about the size of Earth, but it contains the mass of our sun. That makes them incredibly dense. A teaspoon of white dwarf material would weigh, tons, number of tons. Secondly, their energy output. While initially very hot, they quickly dim compared to their main sequence predecessors. The habitable zone in this system around the star, where temperatures are just right for liquid water to exist on a planet surface, around the white dwarf is much closer to the star. We're talking about distance similar to Mercury's orbit around Sun or even closer. Third challenge is the red giant phase. Any planet orbiting a star that swells into a red giant would likely to be roasted or even swallowed entirely. How could life survive such cataclysm? These factors made an idea of life around a white dwarf seems extremely remote. But science is all about challenging assumptions, and recent discoveries are forcing us to rethink everything. The first hurdle to overcome is that the destructive red giant phase. If the planet is to be habitable around a white dwarf, it has to get there somehow. There are a few scenarios researchers are now considering. One possibility is that the planet, especially the gas giant, could have been pushed further out by the expanding star's strong stellar winds, surviving the red giant phase in a much wider orbit over time. As a star contracts into a white dwarf, these planets might then migrate inwards or just find themselves in a new, closer habitable zone. Another, perhaps more likely scenario involves the formation of new planets or moons after the red giant phase. The planetary nebula that shed gas from the star contains a lot of material. It's plausible that the new smaller rocky bodies could collapse from this debris, eventually settling into orbits around the white dwarf. This is an exciting idea, suggesting a second generation of planets. And finally, the existing rocky planets might simply survive. While Earth might be engulfed by our Sun's red giant phase, planets orbiting slightly further out could endure this scorched, airless, zone or the time of the star. The question then becomes: can they regain habitability? So let's assume a planet is orbiting a white dwarf. What does its habitable zone looks like? It's definitely different from our own. Because the white dwarf are much fainter than our sun, their habitable zones are much closer to the star. We are talking about distances ranging from few hundred thousand to few million kilometers, far closer than the Mercury's orbit to our sun. But here is a kicker. While the initial light from the white dwarf might be very blue and energetic, over vast timescales the light emitted will become gentler. And crucially, these habitable zones can be incredibly stable for billions of years, maybe trillions of years. Remember, a white dwarf is just slowly cooling a body. It's not flaring or undergoing dramatic changes like young stars. This stability is a huge advantage for the development and evolution of life. Think about it. Our sun has about 5 billion years left on the main sequence. A white dwarf could provide a stable environment for life for 10 times that long or even more. That's an immense amount of time for complex life to emerge and evolve. Now, living so close to stellar remnant might sound dangerous. White dwarfs still emit significant amount of high energy radiation, particularly in X-rays and UV light, especially when they are young. This could strip away planet's atmosphere or be lethal to the nascent life. So how could a planet in the white dwarf habitable zone protect itself? The answer, much like we have on Earth, likely lies in their robust atmosphere and a strong magnetic field. A thick atmosphere could absorb harmful radiation. Just as our atmosphere protects us, and a powerful magnetic field generated by the molten core would deflect the charged particles from coming from the white dwarf, preventing atmospheric erosion. Interestingly, for a planet to remain active and maintain a molten core for billions of years, it might need to be larger than Earth. A super Earth, a planet up to 10 times the mass of Earth, could retain its internal heat for much longer, ensuring a protective magnetic field for eons. And for the life might require more time to evolve. So this system will provide sort of a protection and also longevity. For life as we know it, liquid water is essential. So where would a water come in a white dwarf planetary system? The process of star becoming a red giant and then white dwarf is incredibly destructive. Any original water on the planets close in the orbit will likely be boiled away. This means that if the white dwarf planet are to be truly habitable, they probably need new supply of water. The good news is that the white dwarf systems are often surrounded by vast disks of rocky and icy debris, the shattered remnant of the asteroids, comet, and perhaps even planets that didn't survive the red giant phase. Did not remain intact. This debris can be seen as pollution around the white dwarf system, and clear sign that the systems are active and may have active environment. Over time, these icy asteroids and comets could be drawn into white dwarf's gravity, crushing into newly formed or surviving planets and delivering the vital water needed for oceans to form. This process, known as the late heavy bombardment or the secondary accretion, is thought to have brought much of the Earth's water to our planet billions of years ago. So the mechanism is very well understood. This is all theoretical at this point in time, of course, but how would we actually find life or even habitable planets around the white dwarf? One of the most promising methods involves observing the white dwarf's atmosphere itself. As planets, asteroids, or comets fall into the white dwarf, their material is vaporized and become part of the star's atmosphere. By analyzing the light from the white dwarf, astronomers can detect the chemical fingerprints of elements like oxygen, carbon, and even water. Finding an excess of water or organic compounds in a white dwarf atmosphere could be a powerful clue that there are or once were watery life bearing bodies in the system. Another method involves looking for transiting planets. If the planet passes in front of the white dwarf, from our perspective, it causes a tiny dip in the star's brightness. While the white dwarfs are small, and so there are habitable zones are also small, making such transit more likely to be observed. We could then analyze the planet's atmosphere for biosignatures, gases like oxygen, methane, or ozone that are often produced by living organisms. While no definitive white stars habitable planets have been confirmed yet, missions like the James Webb Space Telescope are perfectly suited to make such observations. So, what does this mean for the future? If white dwarf habitable zones are indeed common and long lived, the implications are profound. First, it vastly expands the potential for life in the universe. White dwarfs are incredibly numerous. Over 97% of all the stars in our galaxy, including our sun, will eventually become a white dwarf. If even a small fraction of these can host uh, life or habitable planets, then the number of potential abode for life in the cosmos dramatically increases. Second, it offers a potential long term refuge for life. As our sun approaches its red giant phase, Earth will become uninhabitable. But perhaps trillions of years from now, our distant descendants, if we are still around, might find new home around the dim, stable glow of the white dwarf elsewhere in the galaxy. It's a tantalizing thought, a way for life to persist far beyond the lifespan of its original star. It also suggests that the end of the star's life isn't necessarily the end for its planetary system or any life it might harbor. Instead, it could be a transformation, a cosmic recycling process that creates new opportunities for life to emerge or to endure. Of course, it's not all smooth sailing. There are still significant challenges and many open questions, starting with tidal locking. Planets so close to their white dwarf would stars would likely to be tidally locked, meaning one side always faces the star and other is in a perpetual darkness. This could lead to extreme temperature differences, requiring robust atmospheric circulation to distribute the heat around the planet. Next is the stellar flares, especially in the early white dwarfs. While the stable over long period, young white dwarf systems can still experience occasional flares which could be dangerous to life on the planets. Lastly, the asteroid impact. The debris that was left behind that provides water could also pose a significant hazard, especially for newly forming planets. And above all, there are observational limits. While JWST is powerful, detecting biosignatures on such faint planet remains an incredibly difficult task. Despite these challenges, the scientific community is increasingly optimistic. Each new discovery brings us closer to understanding these intriguing stellar remnants and their potential to host life. The notion that we could one day live around a white dwarf star truly pushes the boundary of our imagination. It forces us to reconsider our assumption about what makes a star habitable and where life can truly thrive. It's a testament to the incredible diversity and resilience of the universe. What once seems like a cold, dead end for stars and their systems now appears to be a potential cradle for new life, a beacon of hope in the distant cosmic future. As we continue to explore, observe, and theorize, the white dwarf habitable zone remains one of the most exciting frontiers in astrobiology. Perhaps one day, future generations will gaze upon a dim, Earth sized star in their sky, knowing that life, against all odds, have found a way to endure. So, friends, what do you think about this subject? Could life survive and thrive around a white dwarf? Let me know your thoughts in the comment section below. And don't forget to like this video, subscribe for more cosmic insight, and hit the notification bell so you don't miss out our next adventure. Thank you for joining on this incredible journey. Until next time, keep looking up.